Now we're going to talk about classification. So this is when we have a categorical outcome as we were talking about before. So still we are talking about supervised learning. We have labeled data, but the outcome we are interested in now is a categorical outcome. Let's say it's a spam filter, spam or not spam. It's predicting, say, risk level. We have three outcome levels: low, medium, high. It's the risk of defaulting on a credit or on a loan. So it's either 1 or 0, or it's a power line fault detection. It's a 0, 1 outcome. So in all these cases, we're dealing with a classification. So we're going to first talk about two-class classification, basically when we have a binary outcome, 0, 1, true, false sort of outcome. And then we're going to also look at multi-class classification. And some of the models we'll be talking about can be extended for multi-class classification. So before we get into the models, we're going to talk about, say, how to evaluate them. So first, let's take a look at the data set that we would be using, say, for classification. Let's say the outcome we're interested in this data set. So this is, say, data on employee retention, basically whether or not they're going to stay with us after 2 years. So the outcome here is whether or not they stayed after 2 years. And we have their age, marital status, gender, degree, and their major. An employee number is going to be irrelevant for predicting the year. I mean, you could include it in the model. It would be an incorrect thing to do. So we want to say, given these inputs, we want to predict whether the employee is going to stay or not stay with us. So stay 2 years, yes or no. So this is going to be a classification problem. Before we get into the models, so how do we evaluate the classification model? So for prediction, for numeric prediction, we had RMSE and the MAE, for example, that we could use to predict, to evaluate the numeric prediction models. Here we're dealing with these metrics: precision, recall, and accuracy first. And we're going to talk about a couple more. So whatever classification model you deal with, it's going to basically give you a prediction of, so say the predicted value is going to, it's possible to produce something what's called a confusion matrix. So the confusion matrix shows you, we're going to use the spam filter example. So the outcomes are spam or not spam. And here we have, on this axis, we have actual. So this is for the outcome. So A basically means this was an observation that was spam, and the model correctly predicted it to be spam. So if I go back to the sample data I was showing you earlier, so again, think of what the classification model does is it takes these inputs, it predicts an outcome. And remember, we were training the models on a training set, right? So we have, say, part of this is used to train the model, and now I have a classification model or a classifier. So now I'm taking another part of this data set that I have not used for training, so basically the testing set. Let me just use the pen. Let's say this chunk of the data set I'm using for testing, just hypothetically. And now I'm providing to the classifier that has been trained, I'm providing these as an input, and it predicts some outcome. I know what the actual outcome is, so I can see how well the classifier has performed. And it, based on what the actual values and the classifier's prediction is, we can create what's called this confusion matrix. So let me, oops. Okay, so the confusion, that's what the confusion matrix is showing. So it says, for example, a number of observations were actually spam and the model correctly predicted it to be spam. B number of observations were actually spam, but the model predicted them to be not spam. C number of observations were not spam, but the model incorrectly predicted them to be spam. And D number of observations were not spam, and the model correctly predicted them to be not spam. So whenever we have a classifier, we can have these two metrics called precision and recall for each outcome class. So in this case, we have two outcome classes. We have a spam and a not spam. And we can calculate precision for the spam class. It's going to be the correct number of observations that are correctly predicted to be spam divided by all observations that are predicted to be spam. So you can help to remember it. Could be, so precision starts with a P, look at wherever we have predicted. So the correctly predicted ones divided by all that are predicted predicted to be spam. If you're calculating precision for the not spam class, it would be D divided by, so D is incorrectly predicted to be not spam, divided by all those that are predicted to be not spam, B plus D. And the recall is, so how we calculate recall is the number of predictions that are correctly classified under that group, in this case spam, A, divided by all those that were actually spam, irrespective of whether or not the model picked them up. So it's going to be A plus B. So precision and recall are two main metrics you want to be familiar with. And then accuracy is irrespective of outcome class. So it's basically the sum of all correct predictions. So it's always going to be the diagonal on a confusion, usually be the diagonal on a confusion matrix. So those are those observations that are correctly predicted spam plus those that are correctly predicted not spam here, and then you divide them basically by all observations, all the number of observations. So if you plug in these numbers, these are going to be the values for precision, recall, and accuracy of the spam filter. One thing to have in mind is that you might not always be given the confusion matrix in this format. Sometimes the spam and not spam, these two rows are flipped. Sometimes actual is over here, predicted is over there. And again, the rows might be oriented differently. So, but whatever format you can, you will always be giving a basic definition of what each row and column is referring to. And again, for precision, always take correctly predicted in a group divided by all those that are predicted in that group. So if it's spam, I'm going to be, okay, A divided by A plus C. This is my precision based on this confusion matrix. And if I want recall for spam class, it's going to be those that are correctly predicted as spam divided by all those that were actually spam. And you will hear the terms true positive and false positive. So it's the same, we can derive all these from the same confusion matrix. So basically, whichever outcome class you consider positive, anything that is correctly predicted positive is going to be true positive. So it's actually positive and it's predicted positive. True positive, it's predicted negative, but it's actually positive. So it's a false negative. If it's a false positive, it means it's falsely predicted to be positive. So it's predicted to be positive, but it's false because it was negative. And true negative is predicted negative, and it's a true prediction because it's actually negative. And then you might see the terms true positive rate, which is the same as recall. In some domains, it's called also sensitivity. These are the same things. True positive rate, recall, or sensitivity are the same. False positive rate is the false positive divided by false positive plus true negative. And it's the same as, let's talk first about what's called specificity. So specificity is the true negative divided by the true negative plus the false positives. So this is also called specificity, and false positive rate is 1 minus the specificity. You could write these out and see how you will end up with the same formula here. And then we have also, of course, a false negative rate, which is going to be the false negatives divided by the false negatives plus true positives. So similar to precision and recall, you can calculate these. So whichever outcome class is considered positive, you can calculate the true positive and false positive rate for that outcome class. You don't have to remember these formulas. You can look them up for the purpose of, say, quizzes or homework. And once you use them for multiple times, you will kind of memorize them automatically. Precision and recall is the ones we're going to use more often for the in the context of this course. And the other metrics we may hear about, they all can be basically derived out of these numbers that you can get from a confusion matrix. So what if we have more than two outcome classes, say the multiple outcomes? So it's not gonna change that much. The confusion matrix is just gonna have more rows and columns. So this is, let's say we have three outcome classes, low, medium, and high. So it was, let me bring the pen and let me highlight the formulas. Okay, so we had this before, now we have added, see, we have more and more outcome class. And so we can calculate those same metrics, the precision, recall, and accuracy. So now precision for, say, the low class. So remember what I was saying, you calculate each of these metrics for whichever outcome class you're interested in. Let's say I want to have precision and recall for the low outcome class. So it's going to be the precision is going to be the correct predictions. So basically observations that are predicted to be low and are actually low, A numbers of them, divided by all observations that are predicted to be low. Predicted to be low. So it's going to be A plus C plus G. How about recall for A? Recall for the low class? It's going to be those that are correctly predicted as A divided by all observations that are actually low. A plus B plus E. What if I wanted the precision and recall for the medium class? It's gonna look like this. It's gonna be those that are correctly predicted as correctly predicted. Oh, there's a typo. This has to be a D. Let me fix it. This has to be D. Okay, and this has to be D as well. Okay, so D is predicted to be medium and is actually medium in the medium risk outcome class, and divided by all those that are predicted as the medium outcome class or medium risk, B plus D plus H. And similarly for recall, so I want the recall for, I'm going to go by actual for the division. So I want those that are correctly predicted as medium and divided by all observations that were actually in the medium risk class or the medium risk group, C plus D plus F. And we have a typo here, let's fix that. So yep, it's gonna be divided by C plus D plus F. Sorry, I was just accidentally copying it from over here. So, and of course you know that now for high, how would it look like? If I want precision for the high outcome class, it would be I divided by F plus E plus F plus I. If I want recall for high, it's going to be I divided by G plus H plus I. How about accuracy? Well, similarly, it's gonna be all that are correctly predicted, irrespective of outcome class. So low, predicted low correctly, so A plus D. So these are observations that are actually in the medium risk group and are correctly predicted as medium risk, and I predicted as high risk correctly. They are actually high risk observations. So A plus D plus I divided by basically everything, sum of all cells. So this is how it's going to look like for a multi-class classifier. So now let's talk about a little bit about the intuition. So what does it mean to have high precision or high recall? So we're going to talk about two different examples. One is the spam one. So if I have say a spam filter that has a precision of 10, like here, let's calculate that. So this is about 55%. Let's just write this down. So if you have, this is about 55% precision, and the recall is, again, this is just a hypothetical classifier. We have about 83% recall. Okay. So recall is high, precision is lower. So how do we think about this? So this is a spam filter. So let's think we have emails coming in and they're gonna either be labeled as spam and be sent to your spam box, or they are not spam and they're gonna come into your inbox. So now if I have 55% precision and 83% recall, that means out of all the incoming emails, a bunch of them are spam. So it's gonna pick up 83% of those. It's gonna miss 17% of actually spam emails. So they're gonna end up in my inbox. The precision is 55. What does that mean? So it means out of all those emails that it labeled as spam and sent to my spam box, 55% of these are correctly labeled. So that means basically 45% of stuff that has been labeled as spam and sent to my spam box might not be spam. So that means this is basically non-spam email in my spam box. So if that's something we would prefer, then we would go with a high recall, low precision spam filter. But which one do you think would be better? Would you rather have a high precision, low recall? So let's think about what that would mean. Let's hypothetically think we have another classifier which gives us 90% precision and has 60%, sorry, the handwriting turns out very bad with the mouse. So we have 90% precision, 60% recall. So that means, I made it just worse, 60% recall. So out of all the incoming emails, some of them are actually spam. It's going to pick up 60% of them. So it's going to miss 40%. So you might end up with, compared to this one over here, so let's say we have two options. We have classifier 1, we have classifier 2. Classifier 1, you might end up with less spam in your inbox. With classifier 2, you might end up with more spam in your inbox. But now when we look at precision, that means, so out of the stuff that this spam filter sent to you, my spam box, 90% of them are actually spam. So I'm pretty sure, let's change that a little bit. Let's make it, to be more convincing, let's make this 95, so that we're happy with precision, pretty happy with this. So 95% precision. So that means 95% of stuff that this filter sends to my spam box is actually spam. So I wouldn't really worry about going and checking my spam box for stuff that's accidentally been sent to it. But this comes at the expense of some of the spam emails ending up in my inbox. So it's reasonable to think, let's say our spam filter is learning. So let's say it's using some machine learning models, algorithms, so it can over time better learn to improve both of these metrics. But in the beginning, it would make sense. So personally, I would rather have this one to have, so if stuff is in my spam box, I am rather, I'm more or less sure it's not spam, it's not actual email, it's spam. But I might still end up with a bunch of spam stuff in my inbox, and I'm gonna label those, and hopefully over time, the model will learn, the spam filter will learn to classify spam emails better. So now let's take another example. So what if the classifier we're using is for identifying malignant or benign tumors? And let me delete all these. So in this case, so the scenario here is, let me do the next one. Okay, this one, because we're talking about positive, negative. So in this case, positive means, let's say positive is, let me write it over here. Positive is malignant, and I do mal, and negative is stands for benign. Okay, so if a tumor is malignant, that means it's cancerous, it's dangerous. You don't want to miss that, or even if it's potentially a malignant. But if it's benign, it's harmless. It won't be dangerous to the patient. So in this case, what would you rather have? Let's have precision and recall here. Okay, so I just added these little so that I wouldn't just doodle around. We have the classifier number 1. This is again, the goal here is we want to see which of these classifiers should we use to identify malignant or cancerous tumors. So this precision and recall is both for the positive class. Positive means, in this case, malignant. Benign is negative. So the first one has 70% precision, 95% recall. The second one has 98% precision, 70% recall. So think about for a moment, you can pause and think about which one would you rather use. So what does it mean to have the first classifier? So it has a precision of 70%. It means if it has labeled a tumor as malignant, it's 70% chance that this is correctly labeled. So it's 30% chance it's not really malignant, it has just labeled it as such. How about the recall though? It's 95%. So that means out of all observations or all patient tumors that are actually malignant, it picks up 95% of them. Okay? So you will just be missing, and remember, let me take out recall was the same as the true positive rate. So the true positive rate is 95%, meaning it only missing 5%. The second classifier, if it labels a tumor as malignant, there's a 98% chance it's correct. But out of all cancerous malignant tumors, it's only picking up 70% of them. So which one would you use? Probably one, right? Because in this case, you might be missing 30% of potentially malignant tumors. That means 30% of them think they're fine, right? And but this is actually malignant tumor, so that it can develop into a late stage cancer. So you don't want to miss, you want high recall in this case. Here you made, it's not perfect still, but better than this one. Let's say we want to go with one option. But we're missing 5%, but the precision is not high, it's lower, but that's fine because this is basically a first layer of screening. So if this is giving us, if this is telling us the tumor is malignant or classifies it as positive, we can then look further, and then the true positive rate, sorry, the precision is low, but that is fine. They can follow up and see if it's not really, if it was a false positive, then they can just release the patient. So we would, in this case, then rather go with the first option. So this kind of gives you an idea of which classifier you would rather use in which cases. So maybe for an email spam filter, you would prefer 2, but if it's used to identify very consequential high-risk situations, maybe you would rather do classifier 1. So let's go ahead and talk about some other evaluation metrics. So the ones that so you're gonna see what's called receiver operating characteristics, and another metric that's calculated out of this ROC, basically the area under this ROC curve. So this is basically what these metrics or these plots show us. It's plots the true positive rate. So we had it over here. So this was the true positive rate and false positive rate. Let's go back. Sorry. So it's going to plot the true positive rate for different false positive rates. The benefit of this is having the ROC curve shows us how the performance of a classifier for different classification thresholds. So this is basically how we would read this is here, this is a decision threshold. For example, we could go with, let's say this is about 0.1 false positive rate and a lower true positive rate. But if I want a higher true positive rate, it comes at the cost of a higher false positive rate as well. So oftentimes if you have to make there's a balance between if you want a higher true positive rate, you're gonna get a higher false positive rate as well. Other points of the ROC curve and the corresponding AUC you can calculate from it or get from it is that first of all, we use it when we have balanced outcomes. So I'm gonna draw it. Oh, first of all, before I forget, so how do these compare to a random guess? So if you would have had a random guess on this chart, it would look like something on either of these. I'm just gonna draw it over here. So it would be a diagonal line, something like this. So this would be a performance of a random guess. So instead of having a classifier, if you would just randomly flip a coin, this is the performance you would get. But this should be a flat line, by the way. And how would a perfect model look like? So basically a model that would always correctly predict the positive outcome class. It would look something like this. Again, sorry for the bad drawings. So perfect model, which is in practice impossible, would look like this on this graph. A random guess would look like this. So you would end up, your classifier's ROC curve always would end up somewhere here. And let's go back to the pointer. I said it's good for balanced outcome. What does that mean? So this means the outcome class that we're interested in, for example, we have about equal number of positives and negatives. If you're dealing with a very imbalanced outcome, for example, you're building a classifier for a kind of rare event, let's say classifying fraudulent transactions. So fraudulent transactions are an example of a very imbalanced outcome. So the data set you will be training on is not balanced most often. So in those cases, this is you probably would want to use something else to evaluate the model. Benefits, the desirability of basically the AUC particularly is it measures, I've also put these on the slide notes, it measures how the predictions are ranked, not just their absolute values. And it's called what's known as classification threshold invariant. So it's scale invariant basically. But again, these might not, if you have an imbalanced outcome, you will want to look at what's called, so another curve that could be useful is the precision recall curve. So the precision recall curve is, first of all, you plot it, so similar to the metrics themselves. So we had a precision and recall for each outcome class. So we will have a separate plot for each outcome class. So in this example here, you see you have one for the B outcome class, one for the A. So think of them as low or high, or spam or not spam, doesn't matter. So we have, say, two outcome classes. We have plotted this precision recall curve for both of them. And what are we looking at? So we have basically plotted the precision against the recall. So it's gonna tell us if you want, say, 0.8 recall, if you want a higher recall, it's gonna come at the cost of a lower precision. But if you're happy with low recall, it can give you 100% precision, but that comes at the cost of a low recall, or the other way around. So it says here, for example, you can get a perfect recall, but then your precision is going to just be 40% for, say, the B outcome class. And this is also a good tool, particularly when we have imbalanced outcomes. So we will basically plot this precision recall curve for whichever outcome class we're interested in, and this gives us a good overview of how the classifier is performing. And so what do you think would what would the precision recall curve of a random guess look like? Let me do it with red. So if I would, instead of a classifier, if I would just flip a coin to classify an observation to either of the outcome classes, then its precision recall curve would look like this. What if I had a perfect model? It would be something like always precision is 1 no matter what recall. That would be how a perfect model, of course hypothetically we don't have such a thing, look like the precision recall for such a model would look like. Okay, this is on precision and recall curves. So now we talked about model evaluation. Next, we're gonna get started with the first classification model.